Welcome to Study Loop.
Okay, we have the following ice table and reaction. And so let's just fill out what we can for the rest of this ice table. Um, okay, so what do we know about the change in sodium chloride as the reaction moves forward? Right, so we know that we're going to lose sodium chloride, right? And specifically, we're going to lose two sodium chlorides. How do we know this? Because there's a 2 out in front of sodium chloride, and I don't have sodium chloride in my products. Okay, so the change in sodium chloride, we don't know exactly how much we're going to lose. That's what we're looking for. This number, and we'll just call this number X, right? We just know we're going to lose 2X sodium chloride, right? So we're basically just saying we're going to lose 2 of some number, right? And that same number is the number of copper iodide molecules we're going to lose, right? It's like saying for every, I should say minus, right? For every unit of the reaction that goes forward, we lose 2 sodium chlorides and 1 copper iodide. And we want to find the number of units that the reaction goes forward. Like how many times does this reaction happen going from left to right? And X is that number of times. Every time this reaction goes forward, we lose 2 molecules of sodium chloride. So in the end, if we do the reaction X times, we're going to lose 2 times X molecules of sodium chloride. So that's how we know we can just use X, because we're looking for this X. Like this X is part of our answer eventually. On that note, then, how many copper chlorides should we expect uh, to change each time the reaction happens, right? Well, it's a product if we move from left to right. So this time we're going to get plus 2X, right? And for our sodium iodide, we're just going to get plus X, right? So each time the reaction happens, we lose 2 sodium chlorides, we lose 1, we could put 1 here, 1 copper iodide, we gain 2 copper chlorides, and we gain 1, we could put a 1 here if we wanted, sodium iodide. Okay, so then at equilibrium, it's just going to be the initial plus the change. Okay, so all we have to put here is 0.006 minus 2x. And then here we just have to put 2x, and here we just have to put x, right? Because we started with 0, so equilibrium. We should expect to just have however much the reaction went forward, essentially. Now, the thing is, here we know, or we can calculate what x is. Why do we know this? Well, look at this formula here. And then look at how kind of different it is for copper iodide. We're saying that at equilibrium, we should have our initial amount plus our change, right? That's basically what we did. We said equilibrium equals initial plus change. Okay. Well, for copper iodide, we know what equilibrium and what initial is, which means that we can find change, right? We can plug in 0.007 molar, and we know that that's equal to 0.009 molar plus the change, or minus x. And if we do a little bit of algebra, we can find by subtracting 0.009 for both sides minus 0.009 molar for both sides, we get negative 0.002 molar equals negative x, or 0.002 molar equals x. So now we know that x is equal to 0.002 molar, right? Which means we can find what these equilibrium uh, values actually are. Why is that useful? Well, remember, we're looking for KEQ, which is products over reactants, right, at equilibrium, right? It's these values. we need to know these values to calculate KEQ. Okay, so now that we know what X is, we can actually figure out what the real equilibrium values are, not just the the expression for them, but the real value. What do I mean by that? I mean, if we know that X is equal to 0.002, then we know that this is 0.006 minus 2 times 0.002, right? Which is equal to 0.002 moles. Okay, we already know what this one actually is, right? We were given that. We know that this value is just 2 times x, so this is 0.004 molar. And we know that this is 1 times x, so 0.002 molar, right? Now we have values, equilibrium values, for every concentration in our expression, okay? Expression for KEQ, right? KEQ equals, and then we do the products, concentration of the products raised to their stoichiometric coefficient. So it's going to be concentration of copper chloride squared times concentration of copper iodide. Its coefficient is 1. So we could say raised to the first power, but that's the same thing as just not raising it to anything. Basically what I'm saying is we can do CuCl2 squared, and I'll put EQ because that's at equilibrium. That means that's that value. And right here, I will put, what is this, sodium iodide. Sodium iodide. Okay, its stoichiometric coefficient is 1. Anything raised to 1 is the same thing that it was before being raised to 1 at equilibrium. Okay, and then down here, we're going to have sodium chloride squared and copper iodide. Sodium chloride and copper iodide. Okay, both of these are at equilibrium, and we know what these equilibrium values are now, right? That's what this is, that's what this is, that's what this is, that's what this is, right? So this is going to be, for copper chloride, it's going to be 0.004 molar squared. For sodium iodide, it's 0.002 molar. For sodium chloride, it's 0.002 molar squared. And for copper iodide, it's 0.007 molar. Okay, and then we just need to put this into a calculator. And times 0.002 divided by 0.002 squared divided by 0.007. I get 1.143. And it's unitless, right? Squared moles, moles, or molar. Okay. Unitless value.